Hello and welcome back, everybody. Here we have another example of kinetics of rigid body. In this problem, we have a cylinder with known mass and radius. It is released from rest on an incline as shown. It rolls in such a way that motion occurs with no slippage. The question is, what is the angular acceleration of the cylinder and how long will it take for it to travel 5 meters down the incline? Observe that I already went ahead and drew a diagram representing the key vectors. On the left hand side diagram, on the free body diagram, I have shown this is FBD free body diagram. All external loads, weight of the cylinder mg, normal force exerted by the incline on it n, and friction force tangent to the incline represented by F. On the right hand side diagram, which I call mass acceleration diagram, I have two vectors due to inertia of the cylinder, max due to translation motion of the cylinder and I alpha due to rotation. Observe that if you want to consider kinematics of this object, it is rolling without slippage. So the type of motion that we're concerned with here is general plane motion, which is combination of translation causing acceleration ax and rotation causing acceleration alpha, rotational acceleration alpha. So since I have no slippage, I can then write the linear acceleration ax as r alpha. Observe that I already chose orientation of my coordinate system represented by the blue dotted lines. So x is along the incline and y is perpendicular to it. As far as kinetics of the situation is concerned, I can consider three equations of motion. Net force in x direction equal to max, net force in y direction equal to may, which is 0 because there is no motion in y direction. And lastly, the moment equation, the most important equation in mechanics. Observe that I can take moment about any point. I can take moment about center C, which is what you see in the PDF solution. But here I want to show you a different approach, something to add to what you see in the PDF solution. Since I'm interested in the determination of alpha and I'm not interested in unknowns n and f, I benefit if I eliminate the unwanted unknowns if I take moment of everything about point A. Let point of contact of the cylinder with the incline be represented as point A shown on this diagram. Then if I take moment of everything on the free body diagram with respect to point A, that has to be equal to the net moment of all vectors about the same point on mass acceleration diagram. And I choose to consider clockwise as positive. Typically we take counterclockwise as positive, but since rotation is clockwise and linear acceleration is down the plane, I choose to go with clockwise being positive. That way I don't have to consider a minus in front of the acceleration components. So observe that as far as the left free body diagram is concerned, note that this is angle theta, so is this, which is 20 degrees. Weight has two components, one in x direction, which I'm showing by this arrow, that is mg sine of theta, the other in y direction, which passes through point A. Therefore, the only force on the left side diagram which has a moment about point A is mg sine theta, and moment of this force has a moment arm r, so I multiply this by r to have its moment about point A. So that's all I have on the left side of the equation. On the right side of the equation, I have a vector max that has a moment about point A. The moment arm again is r, so I multiply r times max, and I already have a rotational vector I alpha, so I add that in. Now, if I plug the information from equation 1 into equation 2, I then have mgr sine theta equal to mr ax is r alpha plus I alpha. Note that the right side of the equation has the common factor alpha, which is what I'm really interested in here. And if you recall, as far as a mass moment of inertia of a rotational disk or cylinder is concerned, I about axis of rotation is 1/2 mr squared. So if I plug in for I, let's actually erase this I and plug in for I. So I is 1/2 mr squared times alpha. So what I can do is I can divide both sides of the equation by mass m, so m is gone, and I can simplify this equation further if I factor the unknown alpha from the right side. So I write alpha times r squared plus 1/2 r squared, which is 1.5 r squared. So this enables me to solve the equation for alpha and write alpha equal to, let's see, equal to gr sine theta divided by 1.5 or 3/2 r squared. I can simplify this even further and write alpha equal to 2/3 of g over r sine of theta. Plugging in the numerical values, I get 2/3 of g, which is 9.81, over the radius of 0.15 times sine of 20 degrees. So taking a calculator and doing the numerical calculation, we'll get alpha equal to 14.91 radian per second squared, which is one of the unknowns we were looking at. So now from equation 1, I can find the linear acceleration a sub x. And then equation 1 gives me a sub x equal to 0.15 times 14.91, or numerically I get an acceleration of 2.37 meters per second squared. So now at this point we can find the time required for the cylinder to travel 5 meters. If I consider the linear motion of mass center of the cylinder x as a function of time equals to 1/2 at squared. Observe that the initial velocity is 0 since it is released from rest. So I simplified the kinematic equation and wrote x equal to 1/2 at squared. Plugging the values, we have 1/2 2.37 t squared and x equals to 5. So I solve this equation for t, and it gives me a time of 2.11 seconds and that's how long it'll take for it to travel 5 meters. Thanks for watching.